Okay, let's get started. I suggest to begin this lesson with thickness, which is stored as a p-scale attribute, and it is the thickness of points, triangles, and curves. As you can see, thickness has the same options as the mass parameters. The only difference is that calculate uniform mode is based on the average length of the edges in each piece, scaled by the edge length scale parameter, and as for the calculate varying mode, is based on the average length of the edges connected to each point, scaled again by the edge length scale parameter. For thickness, the default is the calculate uniform, because when the thickness is the same over the whole object, it will lie flat, which is what cloth is expected to do. If there is varying thickness in a piece of cloth, where densely sampled areas are thinner, the cloth wouldn't lie flat. You can still choose calculate varying, which automatically shrinks the p-scale in areas with dense triangles and is larger in places with less triangles. Well, now let's open the geometry spreadsheet and check the p-scale attribute. Look, when we tweak the edge length scale parameter, the p-scale value changes. There is a checkbox called Visualize Thickness, which allows you to visualize the scale without sending it through the solver. Now adjusting the thickness will be much easier because we have a visual representation of it. If we set this to 1, then the p-scale will be equal to the edge length. To make sure of this, let's create a grid that is uniformly distributed segments. You see, the spheres touch each other perfectly, but do not penetrate. Generally, you don't want your p-scale to be bigger than your edge length, which could cause self-intersections. Okay, now let's run the simulation and see what we get with this thickness. To prevent this zigzag shape from being distorted when falling, I suggest disabling the drag force. Let's play again. Good, now the shape is preserved, but the cloth slides down. To prevent sliding too, we need to increase the static threshold. Well, now I want to draw your attention to the gaps between the layers. They were transformed due to the large thickness. Let's visualize thickness already in the solver properties. So now it is clear why such large gaps. We can even look at the thickness in the extrude mode. Especially for curves, it is much more convenient to use this mode. Okay, now let's reduce the thickness decently and check again. As you can see, the gap between the layers has decreased decently, but now they penetrate into each other because this thickness is not enough to handle the collision without fail. Vellum works best with a p-scale that isn't too small, but if you need to set a small thickness, then you will have to improve the quality of collision solve. Let's make a 15 the post-collision passes and check again. Here you are. We already have a fairly clean result, but the gaps between the layers are still large. Let's reduce the thickness even more and play again. I will lower the thickness scale to 0.1, then check the result. Again, the thickness is not enough to handle the self-collision without fail. To compensate for this, it will be necessary to increase the post-collision passes further. Let's make it 40 and check again. You see, what a clear result we got, no penetrations at all, while there are almost no gaps between layers. Okay, let's move on. Now I want to show you what will happen if you put a p-scale greater than the edge length. So now the p-scale, 3 times larger than the edge length. Let's also turn on thickness visualization in the solver properties and run the simulation. You see, after the first frame, the thickness immediately decreased. Vellum records the original distances into attributes and uses those to reduce the p-scale, not to have failed self-collisions initially. As a result, the explosion is prevented. I also want to draw your attention to sharp corners where the p-scale even smaller to prevent any self-penetration there. That is, setting a too large p-scale likely won't blow up the cloth, but it will do collision tests with the large p-scale. Now pay attention to the gap between the cloth geometry and the collision object. In this case, the solver already takes into account the distance we specified. Well, now I want to show you one more important thing related to thickness. First, let's pin all the center points so that the cloth hangs from them. Good, now let's run the simulation and look at something interesting. So, let's get closer, then go to the second frame and look at the corner points. As I said, the solver uses the original distances attribute to reduce the p-scale and avoid self-penetration at the beginning, but when the cloth separates, these attributes will be relaxed, so the cloth won't be got back to too close. You see, all corner points that initially had a small radius acquired a large radius, which of course will lead to better self-collision during simulation. Well, that's probably all I wanted to say about the thickness. We can move on. The next thing I want to talk about is triangulation methods, and I have prepared a separate example for that. Let's switch there. Okay, now let's talk about triangulation methods. Distance and bend constraints are usually built on a triangle mesh. Rather than forcing the input to be triangulated, it can be implicitly triangulated. Now let's isolate the constraint stream and then test all three types of triangulation methods. You see? The constraint geometry is already triangulated and the default is set to alternating mode, which attempts to reverse the triangle splitting, so a series of quads have a less regular structure. Now let's switch to regular mode, which simply consistently split into triangles. And finally, the third mode just doesn't triangulate the input implicitly. So now I propose to check how they affect the simulation. Let's start with the alternating mode. Let's pin the endpoints diagonally and run the simulation. Take a look, this triangulation structure produces such a smooth deformation, even though we have a very low-res quadrangle topology. Now let's change the triangulation method to regular and see what we get. You see? What a stepwise deformation we get, and this is due to the fact that now the triangulation structure is directed in one direction only. So, it turns out that, if we pin the endpoints of the opposite diagonal, this should not happen in regular triangulation mode. Here we go, we got a nice smooth result because in this direction, the triangles already give additional rigidity to it. Well, and finally, let's see what happens if we don't triangulate the geometry at all. See, due to the lack of triangulation, the solver cannot preserve the square shape of the primitives, and as a result, they are strongly compressed. Okay, there is nothing more to say about triangulation. So that's all for this tutorial. We are already familiar with all the properties of cloth constraint and most of the properties of the vellum solver. However, there are still many interesting constraint types that we have not studied during this lesson, but what we know is an excellent base for exploring the rest of the vellum. I also want to mention that I plan to release 2 more volumes about vellum and explore all other constraints with their properties and all the nodes related to vellum, but volume 2 and volume 3 will only be released if from your feedback I understand that you like this teaching style, so I ask you to actively leave feedback if you are really interested in seeing the continuation of this project, the purpose of which is to discover vellum fully. So, I hope you enjoy this tutorial and was useful to you. See you.